Welcome! In this session, we'll be exploring LeetCode problem number 548, split array with equal sum. This is an intriguing problem that challenges us to determine if an array can be split into four non-empty contiguous subarrays with equal sums. Let's dive in and break it down step by step. In this problem, you are given an integer array called nums, and the goal is to determine whether it can be split into four non-empty, contiguous subarrays, A, B, C, and D. The key requirement is that the sum of the elements in all four subarrays must be equal. That means the sum of A must equal the sum of B, which must equal the sum of C, and finally, that must equal the sum of D. If such a split is possible, you should return true. Otherwise, you return false. For the input, the array nums will be a list of integers, and its length, n, can be up to 10,000. For the output, the result is simply a boolean, either true or false, indicating whether the array can be split as required. Let's start with an example to better understand the problem. If the input array is 1, 2, 1, 2, 1, 2, 1, the output should be true. Here's why: we can split this array into four subarrays where each part has the same sum. Specifically, we can have A as 1, 2, with a sum of 3, B as 1, 2, also with a sum of 3, C as 1, 2, again with a sum of 3, and D as 1, which also sums to 3. Since all four parts have an equal sum, the output is true. Now, consider another example where the input array is 1, 2, 1, 2, 1, 3. For this case, the output is false. This is because it is not possible to split the array into four contiguous subarrays such that all of them have the same sum. No matter how we divide this array, we cannot satisfy the condition that the sums of A, B, C, and D are equal. Therefore, the result is false. Finally, let's examine one more example where the input array is 2, 2, 2, 2, 2, 2, 2. Here, the output should be true. We can split the array as follows: could be 2, with a sum of 2, B could be 2, also with a sum of 2, C could be 2, again with a sum of 2, and finally, D could be 2, 2, 2, which also sums to 2. Since all four parts have the same sum, the condition is satisfied, and the output is true. To solve this problem efficiently, we need to account for constraints such as the array length, which can go up to 10,000, and the range of possible values for the elements, which can include both large positive and negative integers. Additionally, edge cases like arrays with identical elements or arrays where no valid split exists are important to consider when designing the solution. To solve problem number 548, our goal is to split the array into four contiguous subarrays A, B, C, and D such that the sums of the first three subarrays are equal. This is a challenging task because it requires finding specific split points in the array while ensuring the sums match. One approach we can consider is brute force. In this approach, we exhaustively try all possible partitions of the array by iterating through potential split points I, j, and k. For each combination, the array is divided into four subarrays, and we check if the sums of A, B, and C are equal. However, this method comes with a significant drawback: its time complexity is O, n superscript 3, due to the 3 nested loops required. This makes it computationally expensive and impractical for larger arrays. To address this, we can look at more efficient strategies, such as optimizing the process using prefix sums. Using prefix sums, we can calculate the sum of any subarray in constant time, which significantly speeds up the process. The key insight here is that the array can be split into valid subarrays if we find indices I, j, and k such that the sums of the subarrays satisfy three conditions: the sum of nums, 0, I, equals the sum of nums, I plus 1 ej, and the same sum also matches nums, j plus 1 k, and nums, k plus 1. To implement this, we pre-compute the prefix sums of the array, which allows us to quickly calculate the sum of any subarray by subtracting two prefix values. Then, we use a nested loop where the outer loop iterates through possible values for the middle split point j, and the inner loop checks potential pairs of I and k that satisfy the conditions. This reduces the time complexity to O, n superscript 2, as we only need to iterate through j and validate pairs of indices for I and k. While this is much faster than the brute force approach, it does require additional space to store the prefix sums, which can be a drawback for very large arrays. To further improve the efficiency of the prefix sum approach, we can introduce hashing. Instead of explicitly iterating through all possible I and k values, we use a hash set to store valid subarray sums as we compute the prefix sums. For each index I, we calculate the sum of nums 0 I and store it in the hash set. When iterating through the array to find the middle split point j, we can quickly check if the prefix sum conditions are satisfied by looking up the hash set. This optimization eliminates the need for some nested loops, making the implementation slightly faster in practice. The time complexity remains O and superscript 2, but the use of hashing can reduce the constant factors involved in the computations. However, this comes at the cost of additional space complexity, as we now need to store both the prefix sum array and the hash set. Additionally, hashing can introduce performance variability due to potential hash collisions, which might impact execution time in certain cases. After considering the various approaches, the optimized strategy using prefix sum strikes the best balance between simplicity, performance, and implementation complexity. It avoids the inefficiency of brute force while remaining straightforward to implement. Although the hashing-based optimization can further reduce some overhead, the added complexity and space requirements often outweigh the marginal performance gains. The key takeaway is that the problem revolves around identifying the split points I, j, and k such that the prefix sums meet specific conditions. By pre-computing the prefix sums, we can calculate subarray sums in constant time, making the iterative process efficient. Compared to the brute force approach, this method drastically reduces time complexity while still guaranteeing correctness for moderately large arrays. Overall, the prefix sum approach is the most practical and balanced solution for solving this problem. In this problem, we are tasked with determining whether an array can be split into 4 non-empty contiguous subarrays, labeled as A, B, C, and D, such that the sums of these subarrays are equal. To achieve this, we need to identify 3 split points within the array, P1, P2, and P3, which divide the array into these subarrays. The requirement is that the sum of the elements in each subarray must be the same. For example, sum nums 0 P1 should equal sum nums P1 plus 1 EP2, which should also equal sum nums P2 plus 1 EP3, and sum nums P3 plus 1 En. Additionally, all subarrays must contain at least one element, ensuring they are non-empty. The first step in solving this problem is to compute the prefix sum array. The prefix sum at any index I represents the sum of all elements in the array from the start up to I1. This allows us to calculate the sum of any subarray in constant time using the formula prefix j, prefix I1. By pre-computing these prefix sums, we significantly reduce the time complexity of subarray sum calculations from O(n) to O(1). Once the prefix sums are ready, we proceed to identify the split points P1, P2, and P3 by iterating over potential configurations in the array. To find the split points, we use 3 nested loops to iterate through the indices of the array. The first loop, represented by P1, considers all potential split points for the first subarray, A. The second loop, represented by P2, explores split points for the second subarray, B. Here, we ensure that P2 is greater than P1 plus 1 to maintain non-empty subarrays. Similarly, the third loop, represented by P3, identifies split points for the third subarray, C, ensuring that P3 is greater than P2 plus 1. For each combination of P1, P2, and P3, we calculate the sums of the respective subarrays using the prefix sums and validate whether they are equal. The condition for a valid partition is sum nums 0 P1 equals sum nums P1 plus 1 EP2 equals sum nums P2 plus 1 EP3 equals sum nums P3 plus 1 En. If this condition is satisfied for any configuration of the split points, we can immediately return true since a valid partition exists. To optimize this process, we replace the 3 nested loops with a more efficient approach. By using a hash set, we can store valid indices for P2 corresponding to each P1. This optimization reduces the overall time complexity from O(n) cubed to O(n) squared, making the algorithm more efficient for larger arrays. The use of prefix sums is a key optimization that reduces the complexity of subarray sum calculations. Instead of recalculating sums repeatedly, we leverage the pre-computed prefix sum array for constant time lookups. Additionally, hashing plays a crucial role in optimizing the search for valid split points. By storing valid combinations of P2 indices for each P1 in a hash set, we eliminate redundant comparisons and reduce the number of nested loops. It is also important to enforce constraints on the indices to ensure that all subarrays remain non-empty. This is achieved by requiring that P2 P1 plus 1 and P3 P2 plus 1. From a data structure perspective, the prefix sum array provides efficient subarray sum calculations, while the hash set improves the performance of finding valid index combinations. Together, these optimizations bring the time complexity down to O(n) squared, with a space complexity of O(n), due to the prefix sum array and hash set. When implementing the solution, we need to account for edge cases. For example, arrays with fewer than 4 elements cannot be split into 4 subarrays, so we return false immediately in such cases. Arrays with all elements equal require careful handling to avoid unnecessary computations. Finally, for large arrays with no valid splits, the algorithm must terminate efficiently within O(n) squared time. These considerations ensure our solution is both correct and performant. Here, we begin the Python implementation of the problem. We start by defining a class called solution and a method named splitArray that takes a list of integers, nums, as input. The first step is to check if the length of the array is less than 7, since a minimum of 7 elements is required to split the array into 4 non-overlapping parts. If the condition is met, we return false immediately. Next, we calculate the prefix sum array to efficiently compute sums of subarrays. This array is initialized with zeros, and the first element is set to the first value of the input array. Using a loop, we calculate the cumulative sum for each index, which allows us to retrieve the sum of any subarray in constant time. After constructing the prefix sum array, we iterate over all possible positions for the second split point, denoted as P2. This point must leave room for valid splits before and after it, so it starts at index 3 and ends at N3. Inside this loop, we initialize a set called scene_sums to store potential sums from valid first split points. For each possible first split point, P1, we check if the sum of the first segment, given by prefix_sum, P11, is equal to the sum of the second segment. If this condition holds, we add the sum of the first segment to the scene_sum set, as it becomes a candidate for verifying the third split point later. To complete the function, we now check for valid third split points, denoted as P3. For each possible value of P3, starting from P2 plus 2 and ending at N1, we verify two conditions. First, the sum of the third segment, calculated as prefix_sum, P31, prefix_sum, P2, must equal the sum of the fourth segment, given by prefix_sum, -1, prefix_sum, P3. Second, the sum of the third segment must already exist in the scene_sum set, which ensures that it matches the sum of the first segment from an earlier split. If both conditions are satisfied, we can successfully split the array into 4 parts with equal sums, so the function returns true. If no such configuration is found after iterating through all possible split points, the function falls through to the final return statement and returns false, indicating that it is not possible to split the array as required. Here, we begin by importing necessary utilities and defining our solution class. The goal is to determine whether we can split the given array into 4 non-overlapping subarrays with equal sums. To start, we check the minimum length of the array. Since splitting into 4 parts requires at least 7 elements, we return false if the array's length is less than 7. Next, we calculate the prefix sum array. This array allows us to quickly compute the sum of any subarray using the difference between two prefix sums. The prefix sum array is initialized with the first element of the input array, and we iterate through the rest of the array to populate it cumulatively. Once the prefix sum is ready, we focus on finding valid split points. We iterate over possible positions for the second split point, P2, starting from index 3 and leaving room for the required splits on either side. For each P2, we use a hash set to store sums from valid first split points, P1. A split point P1 is valid if the sums of the first two subarrays, determined by prefix sum, are equal. If so, we add this sum to the hash set for later use. Now, with the sums for valid P1 stored in the hash set, we move on to finding a valid third split point, P3. The loop starts at P2 plus 2, ensuring there is enough space for the remaining subarrays, and continues until N1 to leave room for the final segment. For each potential P3, we calculate the sums of the third and fourth subarrays using the prefix sum array. Specifically, sum 3 is the sum of the segment between P2 and P3, while sum 4 is the sum of the segment after P3. If these two sums are equal and the hash set contains this sum, it means we've found valid split points for all 4 subarrays, and we return true. If the loop's complete without finding such a configuration, we return false, indicating that splitting the array into 4 subarrays with equal sums is not possible. To solve the problem, we start with an example array nums equals 1, 2, 1, 2, 1, 2, 1. The first step is to check the length of the array. Since the minimum required length is 7, and nums indeed has 7 elements, we move forward. Next, we calculate the prefix sum array, which helps us efficiently compute the sums of subarrays. The prefix sum at each index is the cumulative sum of the array up to that index. For example, prefix underscore sum, 0, is simply the first element, 1. Then, prefix underscore sum, 1, is the sum of the first 2 elements, 1 and 2, which equals 3. Continuing this process, we calculate all values in the prefix sum array as 1, 3, 4, 6, 7, 9, 10. With this in place, we begin iterating over possible second split points, denoted as P2, which will divide the array into 3 parts. Now, let's consider P2 equals 3 as the potential second split point. We initialize an empty set called scene_sums to store sums from the first split that meet the required conditions. For the first split point, P1 equals 1, we compute 2 sums, the left sum, which is the sum of elements before P1, and the middle sum, which is the sum of elements between P1 and P2. Specifically, the left sum is prefix underscore sum, 0, which is 1, and the middle sum is prefix underscore sum, 2, prefix underscore sum, 1, which is 4 to 3, also 1. Since these 2 sums are equal, we add the value 1 to scene_sums. Now, moving to the third split point, P3 equals 5, we check 2 more conditions. The right sum, which is the sum of elements between P2 and P3, is calculated as prefix underscore sum, 4, prefix underscore sum, 3, which is 7 to 6, giving 1. The remaining sum, which is the sum of elements after P3, is prefix underscore sum, 6, prefix underscore sum, 5, or 10 to 9, also 1. Both conditions are satisfied, and since the value 1 exists in scene_sums, we return true, indicating that a valid split exists. Let's analyze a different example with nums equals 1, 2, 3, 4, 5, 6, 7. First, we check the array length, which is 7, so we proceed. The prefix sum array is calculated as 1, 3, 6, 10, 15, 21, 28. Now, setting P2 equals 3 as the second split point, we initialize scene_sums as an empty set. For the first split point, P1 equals 1, we calculate the left sum as 1 and the middle sum as 6, 3, which is 3. These sums are not equal. For P1 equals 2, the left sum is 3, and the middle sum is 6, 6, which is 0. Again, these sums are not equal, so scene_sums remains empty. Checking the third split point, P3 equals 5, we find that no valid values exist in scene_sums to satisfy the conditions. Thus, no valid split is found for this configuration. In this case, since no valid splits are found, we return false. Moving to a new example with nums equals 2, 5, 1, 1, 1, 5, 2, we begin by verifying the array length. With a length of 7, we proceed. The prefix sum array for this input is 2, 7, 8, 9, 10, 15, 17. Setting P2 equals 3, we initialize scene_sums as an empty set. For the first split point, P1 equals 1, the left sum is 2, and the middle sum is 8, 7, which is 1. These sums are not equal. For P1 equals 2, the left sum is 7, and the middle sum is 8, 8, which is 0. Again, the sums are not equal. As a result, scene_sums remains empty, and we cannot find any valid values for the first split. When evaluating the third split point, P3, we find that there are no valid values in scene_sums to satisfy the conditions. Without any valid splits in this example, we return false. This concludes the walkthrough of the solution, demonstrating how the approach systematically evaluates possible splits and determines whether the array can be divided with equal sums in the required format. To understand the time complexity of the solution, let's break it down step by step. First, we calculate the prefix_sum array, which involves a single pass through the input array nums. Since we iterate through nums exactly once, this step takes n time. Next, we have the outer loop where the second split point, P2, is iterated from index 3 to end 4. This means the loop runs approximately n times in the worst case. Now, within this outer loop, we have the first inner loop for finding the first split point, P1. For each P2, this loop checks indices from 1 to P2, leading to up to P2 iterations per P2. When summed over all P2 values, this results in a series that simplifies to n squared. These steps contribute significantly to the overall complexity, and we'll analyze the remaining steps next. Now, let's look at the second inner loop, which focuses on finding the third split point, P3. For each P2, this loop checks indices from P2 plus 2 to n2, which involves around n P2 iterations per P2. When summed over all possible P2 values, this results in a total cost of n squared. Additionally, we use a set called scene_sums to store valid sums during the P1 loop and check for matches during the P3 loop. Since set operations like insertion and lookup are 1 on average, their contribution is relatively small compared to the nested loops. When we combine all these steps, the dominant factor is the nested loops for P1 and P3, leading to an overall time complexity of n squared. Turning to space complexity, the solution uses a prefix_sum array to store the cumulative sums of the input array. Since this array has the same length as the input array, it requires n space. We also use a set called scene_sums to keep track of valid sums during the P1 loop. In the worst case, this set can grow to store one sum for each possible P1, which means it requires n space. Apart from these, a constant amount of space is used for variables like P1, P2, P3, and the loop counters. When we sum up all these contributions, the total space complexity of the solution is n. Let's compare this optimized solution to a brute force approach. The naive method would involve iterating over all possible combinations of split points, P1, P2, P3, and verifying the conditions for each combination. This requires 3 nested loops. P1 ranges from 1 to n6, P2 ranges from P1 plus 2 to n4, and P3 ranges from P2 plus 2 to n2. For each combination, verifying the conditions takes 1 time. The overall time complexity of this brute force approach is therefore n cubed. In contrast, the optimized solution reduces the complexity to n squared by leveraging the prefix_sum array to compute subarray sums in constant time and using a set to track valid sums efficiently. This improvement makes the algorithm scalable for larger input sizes. To wrap up, let's analyze the best, average, and worst-case scenarios for this algorithm. In the best case, a valid split is found early, allowing the algorithm to exit after processing only a few iterations, though the worst-case bound of n squared still applies. In the average case, the algorithm processes a significant portion of the loops before either finding a valid split or concluding that none exists, resulting in a time complexity close to n squared. In the worst case, the algorithm iterates through all possible split points without finding a valid split, which happens when no valid split exists. This worst-case scenario also has a time complexity of n squared. Mathematically, this behavior is explained by the nested loops. The outer loop runs n times, and the inner loops combined perform n operations for each P2, leading to a total of n equals n squared operations. Thus, the overall time complexity is n squared. When working on this problem, there are several common mistakes to watch out for. First, incorrectly calculating the subarray boundaries is a frequent issue. Remember, the goal is to split the array into 4 contiguous, non-empty parts, A, B, C, and D. Even a small off-by-1 error can lead to invalid splits, so it's essential to carefully validate your indices. Next, overlooking the optimization provided by prefix sums is another mistake. Without this, you might end up recalculating subarray sums repeatedly, which is inefficient and complicates your code. Additionally, some solutions fail to check all possible splits. It's crucial to evaluate every valid division of the array within the constraints, as skipping potential splits prematurely can cause you to miss solutions. Another challenge is handling edge cases. For instance, arrays with fewer than 7 elements cannot be split into 4 non-empty parts, and arrays with all identical elements may behave unexpectedly. Finally, don't assume there's only one valid solution. Multiple splits can satisfy the conditions, so your algorithm should account for this possibility and focus on finding at least one valid result rather than assuming uniqueness. In interviews, solving this problem often requires more than just coding. Understanding key insights can set you apart. Recognizing the role of prefix sums in simplifying subarray sum calculations is critical, as it shows you can identify patterns to improve efficiency. Interviewers may also ask about trade-offs, such as the balance between time complexity and code readability. For example, a brute force solution might be easy to understand but inefficient, while using prefix sums improves performance at the cost of added complexity. Additionally, testing edge cases is a frequent topic. Interviewers might challenge you with scenarios like minimal array sizes, arrays containing negative numbers, or arrays with uniform values. Being able to explain how your solution handles these scenarios demonstrates thoroughness. Lastly, scalability is often discussed. Be ready to explain how your algorithm performs on large input sizes, highlighting its time complexity, whether it's O, n squared, or O, n, and any potential optimizations you could implement to handle scale efficiently. This problem also connects to several related problems that can deepen your understanding of the techniques involved. For instance, LeetCode 560, subarray sum equals k, is a great example of using prefix sums to efficiently find subarrays with a specific sum. Similarly, LeetCode 523, continuous subarray sum, applies prefix sums to check if a subarray sum is a multiple of a given number. Another valuable problem is LeetCode 1248, count number of nice subarrays, which emphasizes the importance of efficient subarray sum calculations in a slightly different context. Lastly, LeetCode 1745, palindrome partitioning for, shares the overarching theme of splitting arrays into valid parts, though it focuses on a different condition, ensuring each part is a palindrome. Exploring these problems can help you build a stronger foundation in array splitting techniques and prefix sum applications, making it easier to approach similar challenges. To solve this problem, there are several approaches you might consider, each with its own trade-offs. The brute force approach is the most straightforward. Iterate through all possible splits and check the sums. While this method is easy to implement and understand, it's highly inefficient, with a time complexity of O, n cubed. For larger arrays, this is impractical. A more efficient approach is to use prefix sums. By pre-computing the sums of subarrays, you can reduce redundant calculations and evaluate all splits in O, n squared, time. This strikes a better balance between efficiency and complexity, though it does require additional space for the prefix sum array. For even greater optimization, combining prefix sums with hashing can speed up the lookup process for valid splits. However, this comes at the cost of increased implementation complexity, making the code harder to debug and maintain. Each approach has its merits, so the best choice depends on the problem constraints and the trade-offs you're willing to accept in terms of performance, readability, and complexity. Great job! We've summarized the key aspects of solving problem number 548, split array with equal sum. Remember the importance of prefix sums and optimization techniques for similar problems. Thanks for joining us, and don't forget to like and subscribe for more engaging solutions. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!